Hello, this is Dr. Castoldi. I wish to give you an introduction to the upcoming solar eclipse, which is pretty much an event of a lifetime. And as we know, the sun seems to disappear suddenly during the day for a short period of time in the sky. And so obviously the ancients had their own mythical interpretations of this event, including, these dragons or giants, demons that were swallowing the sun. And so I researched a little bit of, various cultures. For example, in India, there was this demon that tried to steal the nectar of immortality from the gods and therefore was beheaded. Um, and so it formed, it was like a snake form or a dragon form. So it was split into a head called Rahu and the body called Ketu, which in reality represent the two nodes of the moon, as we will discuss later. So the times when an eclipse happens. And so, mythically, they thought that the head, that this Rahu flying in the heaven, would occasionally swallow either the sun or the moon, giving rise to the, eclipse. But then, having no body, eventually the sun or the moon would come out of it. Similar stories in China, Mongolia, Siberia, again beheaded mythical characters chase and consume the sun and or the moon, and again influence from India in Indonesia, Polynesia. There is also this demon Rahu that consumes the sun. In this case, the sun being so hot burns the tongue of the demon, and so it's forced to spit it out, and so on and so forth. So, of course, that's the way the ancients were coping with these very strange and rare events. Now we know a little bit better, and so we will explore the solar and lunar eclipses. What do they look like? Um, what we are going to actually witness here in Michigan. Is it worthwhile to travel a short distance to Ohio to witness the actual totality? Um, but tools that we can use, simple tools to viewing the eclipse. And otherwise, if you like to sit in your office or on your couch with a computer or your phone, you can view the eclipses streamed live by NASA online. But also, there are solar observatories in space that take tons of data about the sun, simulating the eclipse using a method that I will show you. And so, solar and lunar eclipses. Number one, why do they happen? Why are there different types of eclipses? We have the partial, annular, total eclipses. And also, why are they so rare? The solar eclipses are so rare, while the lunar eclipses happen regularly a couple of times a year. And but also why the solar eclipses, when they happen, they are so short. In a matter of minutes, it's gone. And why do they fall on just a tiny area of our planet? And so this is to show you the fact that while planet Earth orbits around the sun, the moon orbits around Earth, which results in the fact that every month, okay, the moon happens to be right in front of the sun with respect to Earth, or right behind the Earth with respect to sun. And so, why don't we have these eclipses so often? Um, well, the story is that the orbit of the moon is inclined by an angle of 5.2 degrees with respect to the orbit of the Earth around the sun, the ecliptic. Therefore, it's rare that there is a complete alignment. It only happens where the orbit of the moon crosses the orbit of the Earth. And so here is a rendition of that. We call the nodes the 2 points where the orbits cross, and that's when there can be an eclipse. So here is when the demon Rahu, eats up the moon or the sun, and we have the actual eclipse. And so, therefore, as you can see here, just at these two locations, there is perfect alignment of the three bodies. And so, when the moon is full, um, should be full, of course, um, and passes right behind the shadow of the Earth, it gets obscured, giving rise to the eclipse, the lunar eclipse. Similarly, when the moon is in front of the Earth, it obscures. It's a very interesting fact that the location of the moon, which is so tiny compared to the sun, is such that it can cover in its entirety the 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 sun. And so, of course, as you can see, the shadow of the moon just goes onto a tiny portion of the Earth. And therefore this would happens when the moon is new. So the moon receives light from the sun on the other side, on the side that we cannot see from Earth. Now, a couple of things about shadows. Simple geometry, if you have studied a little bit of art, when a lamp or so sheds light on a small object, there is this game of rays that produce either a complete, darkness, but also surrounding it, there is another region which is partially obscured of shadow. So we call, using Latin words, umbra, which is shadow, the one indicated in black, the complete darkness, or the penumbra, the one that is partially darkened. Okay, so the remember this. Okay, so now the next thing is that as we know, the moon is only 1/4 of the diameter of planet Earth. So the shadow cast by the Earth on the moon covers it in its entirety. And so, of course, then the moon is moving at the rate of about an hour, one 10 degrees or so in the sky for every hour. Um, so if we look at the sequence of the three pictures going from the bottom up, the moon in its orbiting, around the Earth passes initially through the penumbra. So the moon gets more like a grayish color. Then it starts entering the umbra region, and so part of it begins to disappear. And only when it is completely inside the umbra region at the top, it gets this strange orangey color. So why all of a sudden the moon that should be completely obscured is lighting up? And it's simply because of the reflection of some of the light received by the Earth, and that the atmosphere around the Earth creates this effect of reflecting some of this light that gives this unbelievable color to the moon. So once again, that happens when the moon is full, that is, it passes behind the Earth. Now, conversely, the Earth is like a speck of dust compared to the sun. This photo, shows the unbelievable difference in size. And so the Earth is only 100, the sun, the diameter of the sun is 100, times or so the diameter of the Earth. So it's huge. So how can the moon cover it? Well, the story once again is that at this particular time, the moon is at a location, can be at a location where it completely shadows the entire, sun. It doesn't always happen 100%. So even if the moon is at the nodes, the orbit of the moon is slightly elliptical, and so it may be a touch closer or a touch farther from the Earth, giving rise to, either the total solar eclipse when the moon truly reaches the umbra of the moon reaches, the Earth. But if it doesn't, as shown at the bottom, it we can enter the penumbra, but the umbra is not reaching Earth. Therefore, we have an annular solar eclipse. We still see a ring of the sun. And then, of course, in between there is the partial solar eclipse when, once again, as the moon moves around, planet Earth, it begins to obscure the sun until then it reaches total solar eclipse. And so just to show, these are views from satellites of solar eclipse. And so as you can see, of course, the moon is so small that it obscures the only a very small area of the Earth. And so indicated by the arrows are the umbra region and the penumbral region. Still, both are pretty small. That's why it's so rare to see an eclipse at your location. So if you remember, we just had one crossing the United States in 2017 that is shown at the top, and then the current one that is more like a south-north, eclipse. Other eclipses most often happen in the Pacific, in the oceans or so, or of course in other countries. Um, Therefore, there are people who like to study the eclipse who do all these trips, at times to tiny islands in the middle of the Pacific just to catch it. But if you are stable in an area of a country, it's a fairly rare event. As you can see, coming up again through the United States, but not our area, there is another eclipse in 2045. And here is a better rendition from the greatamericaneclipse.com website. So the 2024 crosses north-south. We have to wait for 2045 for an east-west, but farther south, eclipse, etc. 2078, 2099. So they are rare events, although on average, every year and a half or so, there is a solar eclipse, but somewhere on Earth, not at our location. That's why typically they say that the solar eclipse is an event of a lifetime. Just to say, total solar eclipses visible across the USA were in 1918, 1979, 2017. So pretty rare events. Now, the other question I had posed is, okay, once we finally get, in our area, a total solar eclipse, why is it so short? It's always just a matter of minutes. In particular, the 2024 totality, at its best, as we will show, lasts just a touch less than 4 minutes. So all this ordeal to just have an event that is so short. Why so? Because we cannot forget that the Earth rotates about its own axis and it goes pretty fast. So the shadow that the sun casts, the moon, sorry, casts, on one this little location of the Earth also moves pretty fast, and therefore the solar eclipse is gone so quickly. Now, what does a solar eclipse look like? So I'm going to show you the sequence and some of the beautiful effects. That's why people are so enthusiastic about witnessing it. And what we are going to see here in Michigan, and so on. Catching totality, if we want to travel a little bit to Ohio, that's our chance. So the sequence, this is a composite photo of many photos that shows the sun that starting from the top at some point in the afternoon is going down, towards sunset. And we can see the orb of the sun, gradually decreasing, more and more darkness around it, then this sudden explosion of light, and then starting on the other side, the shadow starts moving out until when the sun is nearly set, is back to full, the full disk. Here is another rendition of that, and the you want to set a time aside, a couple, 2.5 hours. You will not be staring with your nose up, looking at the sun all the time, but every few minutes, every 10, 15 minutes, go out and see what's going on. And so it starts in our area at 1:58 p.m., reaches totality around 3:14 p.m., and then, you know, ends completely at 4:27 p.m. But where does it reach totality? Actually, not where we are. Very close to us, but not where we are. We are just outside that area. And so we will only witness about 98% covering of the sun, but not the complete totality. Now, what would we see? When the it will just a touch before totality, you start seeing this beautiful diamond that is due to reflection, of the surface of the moon. It's all an optical effect due to the fact that the moon is not a perfect sphere, but it has mountains and depressions, etc. And so this ring also, once again, pretty quickly disappears, and then we start seeing this whole area, the so-called corona, that surrounds the sun, which again then disappears fast, and we go back to this diamond effect, and then to seeing, the beginning of a illumined part of the sun. So the corona is unbelievably beautiful, and we can only witness it at perfect totality. Why so? Because when we look at the sun, we are only seeing, because of temperature effect in the visible, the sun looks like this yellow orangey. Actually, there is actually a touch of green also that goes unnoticed in it. So the photo on the left is a photo using a telescope of the sun with these little spots that you probably know, the dark spots. But then the sun is surrounded by an enormous amount of very hot radiation that reaches millions of degrees, but that is rarefied, so we don't see the rest of the surface of the sun. It's much brighter, and therefore we normally see just, the round disk of the sun. And so at totality, when the sun is, you know, completely covered, then we see these beautiful jets of, radiation and gases. And if you look in detail at this photo, you see some tiny red spots, which are prominences, because the sun is not just a hot ball, but it's like a boiling pot in which, this radiation and gases move. And so where will this eclipse cross? It's going to cross south to north. So it starts on the west side here in the Pacific, reaching Mexico and then coming north through a variety of states, hitting our neighborhood, if you wish, moving to northeast Canada and later in the Atlantic. There are maps that are printed that show where the totality is. And so we can see in this drawing the green parallel lines representing the amount of coverage of the sun. And so as you can see, the region that is Pontiac listed, in our region, only about 98% of the sun will be covered by the moon. So we need to go to Toledo in the list, or south of Toledo, or the way down a little further, down around the lake to witness the totality. And there are also listed how many minutes of totality we would witness. And so I investigated, for example, I have a friend that lives in Perrysburg, which is a southern suburb of Toledo, right where the Route 80 passes. And there is only about 2 minutes of totality. So we would have to go towards, either Bowling Green, Fremont, Sandusky, to get closer to the longest amount of totality, which is about 3 minutes, 40 seconds, or even more, going towards the Cleveland or so. And so what to expect? The sun will start, so the sun is gradually going down, setting in the west. So we are looking in the west where the sun will be around 2 p.m. And so it will start at the altitude of about 55 degrees above the horizon, and then go all the way down to about 38 degrees above the horizon. And again, it starts, at 1:58 p.m., ends at 4:27 p.m. But the time to really watch the sky is around, 3 to 3:30 p.m. And in this figure also, the dark figure is the shadow of the moon that is moving because the earth rotates. If you want to also kind of get an idea of what you are going to see, then go to this time and date website and choose, actually I already chose for you Detroit, or you can choose some other town in case you're out of town, and see what to expect. Okay, it's a simulation of the eclipse. And the only factor, of course, we are in Michigan and Ohio is not very different. Uh, what about the weather? This is April. Last eclipse in 2017 was in August, where the you know probability of sunshine, is fairly high. But what about early April? Well, I found this map on the Astronomy magazine that shows that we are to expect, of course, Cleveland is a little past where we are, so we are going to expect somewhere between 60 or 70% coverage. That's a typical cloud coverage that's typical of this month of April around, the 3 p.m. time. So it's a matter of luck. Hopefully, the weather will collaborate and we will be able to witness the eclipse. Here again, this is actually a photo from satellite of cloud coverage expected around this time of the year. This photo was taken exactly a year ago on April 8th. And so, it's possible, but, there is this degree of uncertainty. Um, So if we want to catch totality, I've circled, a couple, two, three towns. Of course, Toledo. My first thought was to go to the area in the northern part of Toledo where the University of Toledo is, and that would be a drive of about an hour 20 minutes, actually from the Oakland. If you go and an extra half hour or so, you hit Bowling Green, where the totality, and actually again in Toledo the totality is only about 2 minutes, but if you go down a little further to Bowling Green, it's about 3 minutes of totality, and in Fremont, 3.5. Excuse me, 3.5 minutes. So the only thing is, be aware that you are not the one and only person that wants to witness the eclipse. There will be lots of traffic. So if you decide to travel, do it early in the day, making sure that you allow plenty of time both to go and to come back. Now, what to do? Well, of course, they sell this very cheap. It's usually $2, $3 Eclipse glasses. They are not really glasses. It's a film. It's a metallic film that stops lots of the radiation that comes from the sun, preventing your eyes, from getting ruined. Um, at the same time, even if you use the Eclipse glasses, you will not be staring at the sun for 3 hours. You will look, then, maybe pass the glasses to a friend and so on. So, you can look for a brief amount of times. Another safe way is to project the sun. So there is such thing as a sun spotter, which is actually kind of expensive, that projects to a hole the sun, on some paper. You put it on the floor and does that. On the other hand, you can make your own very cheaply. So all you need is two pieces of cardboard. In one, you draw, a pin-size hole, and it acts like a camera that projects. So you direct the thin dark cardboard, for example, from a cereal box to the sun, and project it. You can see where its shadows is, and so on the floor you will put a white cardboard or white paper, and the sun, or the eclipse, anyway, will be projected onto the one on the floor. So the photo, shows what you would be see. So you are looking indirectly at the sun. You are not looking at it, but you are looking at the projection. So it's safe, even if you don't wear glasses, sunglasses. Um, so another way, if you own binoculars or a telescope, is to surround it with a thick cardboard, as shown, in brown. And then again, in no form you look through the telescope or the binoculars, but you point it to the sun and again use the projection. So you project that on a white cardboard or white paper. And again, the photo here shows the beautiful, image of the beginning of the eclipse, on the grass. Okay, so never, never, ever look through binoculars, telescope, or anything, and never, ever, ever look directly at the sun. We know the story of the great Galileo Galilei, who did the first telescopic observations of the sun, discovering the sunspot, and he paid for that, becoming blind. So we do not want to risk to burn the retina of our eyes. So don't do anything stupid like just using your regular sunglasses. You can even pile up 10 sunglasses that will not stop enough of this radiation coming from the sun and will not prevent the generation of your retina. Similarly, if you want to take photos, there are solar filters that you can buy for cameras, which are much stronger than the you know, Eclipse glasses. So what this person is doing, just using regular Eclipse glasses to take a photo, is absolutely no. You once again, in all these cases, you are going to create problems for your eyes. Now, the other thing is for those who don't really like to go places, well, NASA, just like they did for the 2017 eclipse, will stream the eclipse live. And not a whole lot is published yet, but if you go to this website at the right time, we'll show you the images taken by various observatories. There are solar observatories around the world, and or satellites of the event. Now, another interesting thing is that we have seen that we see aspects of the sun, the corona, that are not normally visible even to telescope. So the scientists have created this simulation of a telescope, the coronagraph, that is allowing us to view the corona of the sun by covering the disk of the sun, which is very simple, but not so much when we think about the fact that once again the Earth rotates fairly fast. I did an observation of the sun several years back with a telescope that, of course, had the filter to watch the sun, and the sun would go out of view so quickly. I mean, we are talking in a matter of seconds. So the sun moves fast in the sky, describes 180 degrees in 10, 12 hours. And so this coronagraph needs to constantly cover, move and to cover the disk of the sun. And so then we see like these images from the SOHO Solar and Heliospheric Observatory, um, that these enormous ejections of energy, radiation, etc., from the sun. So much more is going on the sun than it catches the eyes. And by the way, if you look at the photo the colors are, irrelevant. If you look at the left inside one, you can actually see two streaks in the bottom, which are actually called comets. And so this is just to give you a better rendition. I'm sure you have seen this in the Facebook, that the sun is ejecting prominences, so ejecting gases and radiation at great speed. And at the bottom, for reference, is the size of planet Earth. So these are enormous ejections. And also filaments are similarly, you can see the color representing, you know, a much higher temperature than the rest of the surface of the sun. And of course, the darker regions are, it's a whole, up-down movement of these gases. And so the gases coming up towards the surface are lighter, are hotter, and therefore they look lighter. The ones that are re-entering down in this convective motion down towards the inner part of the sun look darker. because they have cooled and now they're falling back. Here again, another dramatic view of the sun. And again, what these prominences are, we have linked them to the sunspots and to the fact that the sun has a strong magnetic field, and therefore these gases that are ejected follow the lines of the magnetic field and then come back into the sun. And so the two spots from which this arch of material comes out and goes back in are what we call the sunspots, which are a tiny bit cooler than the rest of the surface. Therefore, that's why they are here dark. And again, as a reminder, we are more or less at half of, we're approaching the highest point of solar activity. We have studied that the sun reaches periods of maxima and minima. Again, this is all linked to the effects of the magnetic field of the sun that wrapping around splits at points where gives rise to the sunspots. So at the solar minimum, the number of sunspots is minimal, as shown on the left hand side, towards the maximum, which should be around 2025. The number of sunspots gradually increases to a maximum to then decrease again. So that's also something to keep in mind, that more solar activity, also more disturbances to the various satellites that are surrounding planet Earth, helping us, with variety of communications on the Earth. This data is from High Node, another observatory. So if you want to know more, there is data from SOHO. There is data from the Solar Dynamic Observatory, which is a little bit more recent than SOHO, and then High Node, which is a NASA and Japan collaboration.